In section 4.1, we're going to be talking about polynomial and rational functions. In this section, we're going to divide polynomials, we're going to talk about the remainder and factor theorems, and we're going to determine the maximum number of zeros of a polynomial. So first of all, let's talk about a polynomial, which is an algebraic expression that can be written in the following form, and that form would be something like this: f of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus a sub 1 x to the 1 plus a sub 0, and then x to the 0, which is just this whole value here is 1, so we don't need it. That looks a lot more complicated than what it is. Really, it's just saying that these are going down, the powers of x are going down by 1. So something a little easier to think about might be something like 2. And these could be any values here. This would be the leading coefficient, x cubed plus 1/2 x squared plus 3x minus 5. And so this is just your constant that compares to this here. And the key here is that n is a non-negative integer. So that would be this n value here. So the characteristics of a polynomial function are that all exponents are whole numbers. No variables are in the denominators, so we couldn't have something like this. We couldn't have that. And then no variable in the radicand, so which sort of goes along with number 1, all of the exponents are whole numbers, because if you have something like this, that is equivalent to the square root of x. And that breaks rule 1, and this breaks rule 2, because x is in the radicand. So now we're going to talk about the different types of polynomials, the first being a constant polynomial. An example would be f of x equal to 8 or any other constant. It could be a fraction as well, so you could have f of x equal to 1/2. You have the zero polynomial, which is just when that constant value is equal to 0. And then the degree of a polynomial is determined by the exponent of the highest power of x. So order doesn't matter here at all. So if we have a function f of x equal to 1/2 x to the 5th minus 3x to the 7th plus 5, then we would say that the degree of this polynomial is 7, because that is the highest power of x. The leading coefficient is simply the coefficient of the highest power of x. So here we go back. Your leading coefficient is going to be this -3 here. And then polynomial functions have specific names. If it is a first degree polynomial, such as y is equal to x plus 3, it's first degree because the exponent, the highest exponent there is 1. That is called a linear. A second degree, if we just change that to x squared plus 3, now it's second degree, and that is called a quadratic. And then similar to that, we have x cubed plus 2x. That's an example of a third degree or a cubic. And then a fourth degree, an example would be x to the 4th minus 9. And that would be a fourth degree or a quadratic. Now we're going to look at an example of synthetic division. Synthetic division is when you are taking one polynomial and dividing it by another polynomial. So I'm taking this polynomial and I'm dividing it by x minus 4. I'm going to use synthetic division. One of the first things you want to look for is to make sure that nothing is missing if you're going in descending order. So if we have 2x to the 4th and then we go to x squared, we need to put in there a plus 0x to the 3rd minus 25x squared minus 30x plus 5. Okay, so putting this piece in is going to be key. Make sure we don't have mistakes. And now to divide by the x minus 4, what we're going to do is we are going to take the opposite of this. Okay, one way to think about it is if you're taking this and you're setting it equal to 0, solving. So that number goes here. And then we're going to take the coefficients of each of the terms. So I'm going to take a 2, and then a 0, and then a negative 25. Make sure you take the sign. A negative 30, and a positive 5. Right? And now what you do is you drop the first number, and that becomes 2. And then at that point, you're multiplying the 4 and the 2, and that gives us positive 8. And then you're adding in line here. And then again, you go back and multiply by the 4. That gives us 32. And then we add in line. Again, we get 7. Then we take the 4, multiply it by the 7, we get 28. When we add, we get negative 2. And then you're taking the 4, multiplying by the negative 2, you get negative 8. 5 minus 8 gives me negative 3. Okay. So we do all of that then to say that we get, after the division process, we would have, you drop down 1 power. So here we had an x to the 4th. So when we have this 2 here, it's 2x to the 3rd plus 8x squared plus 7x minus 2 with a remainder of negative 3. This last value is always the remainder. And now let's talk about the division algorithm. And the division algorithm, this is in polynomial form, and I can do a simpler form. So for example, if I think about just saying 36 can be rewritten as 7 times 5 plus 1. Okay, and that's all this is saying, but it's just talking about in terms of if we have polynomials. H of x would be a polynomial, so the polynomial h of x times q of x plus r of x is going to be equal to our polynomial f of x. And we can give each of those names. We call this, or our 36, the dividend. We have our divisor. We have our quotient, and then of course the remainder. All right. Which leads us to talk about the remainder theorem. And with the remainder theorem, you're trying to find basically a shortcut to find out what the remainder would be. So if you have this polynomial f of x, and it's divided by x minus c, then the remainder is simply just f of c. And here's an example that we can take a look at. We are going to try to find the remainder when f of x equal to, we have a little bit of a mess here, so let's write this, f of x, and the function that I have for f of x is x to the 87th power minus 2x to the 36th power plus 8. And I want to find the remainder when it's divided by x plus 1. So, of course, not something you'd want to do synthetic division for. So if we use the remainder theorem, then we can just find f of the opposite of that, negative 1, if you're solving for that. So again, x plus 1 equal to 0, x equals negative 1. So we're putting in negative 1 here, and so we get negative 1. Make sure you put this in parentheses, to the 87th power minus 2 times x, which x here is going to be negative 1 to the 36th power plus 8. So f of negative 1 then would be negative 1 minus 2 times 1 plus 8. And so f of negative 1 would just give us 5. All right, so we know the remainder in that case would be 5. And now let's talk about the factor theorem. A polynomial function f of x has a linear factor x minus a, and if and only if f of a is 0. So what we can do here is just find out. So the f of a, this piece here, f of a is equal to 0 is coming from here. So if we solve this, then we get x is equal to a. All right? And then that's how we're going to find f of a. And so in this case, this particular case, we have negative 2, x minus 2 equals 0, x is equal to 2. So f of a is equivalent to f of 2. If we plug that in for our function, then we get 2 to the third. I don't have to use parentheses here because it is not negative. 2 to the second minus 2 times 2 minus 24. All right, and now I can simplify. 8 plus 5 times 4 minus 4 minus 24. Take that a step further and simplify, and I get 0. And now we can see that you get 0, and as it tells us if f of a is equal to 0, then what we know is that x minus a, which in this case is x minus 2, is a factor. And now for the last step, all of the following statements about polynomials are equivalent. So to understand these a little better, let's look at a polynomial. F of x is equal to x minus 2 times x plus 2. All right, so as we know, if we sketch the graph of this, it would look something like this. And those are the significant points that we're talking about. So r is a 0 of the function. So we have zeros of the function. And visually you can see the little green circles there that are the zeros of the function. R is also an x-intercept of the graph. So you see that they're the zeros, they are the x-intercepts. And you could get the zeros just by solving each piece of the factor here. X minus 2 equals 0, which gives you x equals 2. And then here, x plus 2 equals 0, so x equals negative 2. So you have the two zeros, you have the x-intercepts, they are the same thing because we remember what we're looking for here is equivalent statements. X equals r is also a solution or a root to the equation. So another name for a 0 is the root. And x minus r is a factor of the polynomial. So while negative 2 and 2 are zeros, x minus 2 and x plus 2 are what we call factors of the polynomial. And then the final piece here is the number of zeros for a polynomial. A polynomial of degree n has at most n distinct real zeros. So for example, the polynomial y equals x cubed, because the power here is 3, its degree is 3, it has at most 3 unique zeros. But of course if you graph that, you realize it doesn't have 3 zeros, it has 1 zero. And that's a possibility too. So that's why here it says, it doesn't say that it does have 3 unique zeros, it says it has at most 3 unique zeros. And that's all I have for section 4.1.